We have seen how logarithms are useful in solving exponential equations. But logarithms are also useful in certain applications. In fact, you may have encountered these specific applications in your everyday life and never known that they were based on logarithms. Logarithms can be used to take a wide scale and convert it down into a smaller, more comprehensible scale. We do this with both the Richter scale, the decibel scale, and even the pH scale. So let's take a look at, first of all, the Richter scale. The Richter scale uses a common logarithm to convert a wide range of seismographic readings into a small scale for measuring the magnitude of an earthquake. An earthquake whose seismographic reading is x millimeters has magnitude m of x equals log of x divided by x naught, where x naught is 10 to the negative third, gives us the reading of a zero-level earthquake the same distance from its epicenter. So what we're going to do is take the measurement from the seismograph, x, measured in millimeters, and we're going to convert that into the magnitude of the earthquake. Now, the magnitude is what you hear on the news. Something like there was a 4.5 earthquake in a specific location. And our function, m of x, is going to convert that millimeter reading into a magnitude. So on example 8, it says, in 1989, a devastating earthquake hit the San Francisco Bay Area, registering a seismographic reading of 7,943 millimeters. Determine the magnitude of the earthquake to the nearest tenth. So we have the seismographic reading and we want to convert it into a magnitude. So our function is m of x equals log of x divided by x naught. And remember, when the function was introduced, that x naught reading was 10 to the negative third. So we can write this 10 to the negative 3. Now, before we answer the question, let's take that 10 to the negative 3 out of the denominator and give it a positive exponent. So we can call that 10 to the third power, or 1,000 times x in the numerator. So 2 steps there. I took 10 to the negative 3 out of the denominator and into the numerator as 10 to the positive 3, and 10 to the third power is equal to 1,000. So now we can answer the question. If the seismographic reading is 7,943 millimeters, we need to find m of 7,943. So this is log of 1,000 times 7,943. Or log base 10 of 7,943 with 3 zeros on the end there, which would be 7,943,000. So let's type this into our calculator. We have log base 10, 7,943, 1, 2, 3 zeros. And we come up with a scale or a score of 6.9. Generally, the magnitude is given to the nearest tenth. So that was a 6.9 earthquake there in 1989. Now, to understand how this function works, or how a logarithmic scale works, let's answer the next question. What would be the magnitude of an earthquake that is 10 times more intense? That is, the seismographic reading was 10 times higher. So instead of 7,943 millimeters, we're looking at 79,430. I just multiplied it by 10 there. So we're going to evaluate log of 1,000 times 79,430. Or for ease of typing this into the calculator, we'll add 3 zeros to our 1 zero to our previous evaluation. So we're going to have log. This time we'll have 4 zeros. And notice this gives us a scale of 7.9. So an earthquake 10 times more intense than a 6.9 registers 7.9. So to our ear, it doesn't sound like much difference. Well, it's only 1 point of difference. But if you're actually experiencing the earthquake, a 7.9 magnitude earthquake is 10 times more intense than a 6.9 earthquake. Now, let's find the magnitude of an earthquake that's 100 times more intense than this one that measured 7,943 millimeters on the seismograph. So we want to find m of 7,943 times 100, or 794,300 millimeters. So plugging this into our function, that's going to be log of 1,000 times 794,300. Or log of, I'm going to take the 794,300 and add 3 more zeros. That's 794,300,000 in our argument. So this will be log one more zero on our answer there, and notice that gives me an 8.9. So if I compare this earthquake to an earthquake that measures 6.9, this one would be 100 times more intense than an earthquake that measures 6.9. If I compare it to an earthquake that measures 7.9, an 8.9 is 10 times more intense. So when the intensity increases by a factor of 10, the seismographic reading only increases by 1 point. But that's important to know as you interpret the news when you hear the magnitude of an earthquake. The pH scale works similarly. The pH scale is used to measure how acidic or basic a substance is. The pH of a certain chemical is given by pH equals negative log of H positive, where H positive is the concentration of hydrogen ions in moles per liter. So we have the pH, which is the scale, and we have the number of hydrogen ions in moles per liter as the argument of our function. Now on the scale here, you can see some common everyday items: lemon juice, an egg, bleach, and you can kind of see where they fall on the pH scale. But the function that describes the relationship between the hydrogen ion concentration and the actual score is a logarithmic function. So with this in mind, let's see if we can answer example 8. What is the pH of a solution for which H positive is 0.1? So our function is pH equals negative log of H positive. So the pH for this solution would be negative log of 0.1. So let's type that into our calculator. Negative log of 0.1. Now we are looking at a base 10 logarithm here. So remember, base 10 log is going to count the decimal places. So there's one decimal place here. So the answer to log of 0.1 would be negative 1. And then our negative coefficient times negative 1 would give us a positive 1. So the pH solution, or the pH score, would be 1 for hydrogen ion concentration of 0.1. What is the pH of a solution for which H positive is 0.01? So in this case, pH would be negative log of 0.01. Negative log 0.01, that's going to be a negative 1 times negative 2, which gives us positive 2. With those two calculations in mind, what happens to the pH of a solution when the concentration of hydrogen ions decreases? Notice in the previous example, we went from 0.1 moles per liter to 0.01 moles per liter. So the hydrogen ion concentration was decreasing there. And notice the pH increased, right? So we can say the pH increases as the concentration of hydrogen ions decreases. So the less number of hydrogen ion that are present in the solution, the more basic the substance is going to be. Example D, determine the hydrogen concentration of an orange with a pH of 3.5. So this time we know the pH and we want to know what's the hydrogen concentration. So once again, the function is pH equals negative log of H positive. This time we know the pH is 3.5. So we need to solve for that concentration. And for ease of notation, I'm just going to call it x. So we need to solve this logarithmic equation for x. So first, let's divide both sides by the negative. So we get negative 3.5 equals log of x. This is a logarithmic equation, so we can solve it by converting to exponential form. Now remember, the unwritten base here for an log log is 10. So I'm going to convert this to exponential form by taking 10 raised to the negative 3.5 and setting that equal to x. 10 to the negative 3.5 is equal to x, or x is equal to 10 to the negative 3.5. So that's the concentration in, as a power of 10, and remember this is moles per liter. Now, if you type this into your calculator, you want to be able to interpret the result. So 10 raised to the negative 3.5 gives me the answer in scientific notation. Okay, so this is approximately 3.16. Notice this e to the negative 4. That means times 10 to the negative 4. That's what is meant by your exponential form or scientific notation. So we end up with 3.16 times 10 to the negative 4 moles per liter. The next question is similar. Determine the hydrogen concentration of human blood with a pH of 7.4. And again, leave your answer in exponential form. So we'll take human blood pH 7.4 and we'll solve for the hydrogen ion concentration, which I'm just going to call X. Divide both sides by a negative and then convert to exponential form. We'd end up with X equals 10 to the negative 7.4. On our calculator, 10 to the negative 7.4 in scientific notation would be 3.98 times 10 to the negative 8. So X would be 3.98 times 10 to the negative 8, and that again is moles per liter. Now on that one, notice that the pH from the first example to the second one increased, and the concentration of ions decreased. So we could say human blood with a higher pH is more basic than an orange with a pH of 3.5, which would be more acidic.